Hello students, my name is Shayan Mitra, faculty member of Department of Electronics and Communication Engineering of Greater Kolkata College of Engineering and Management. Today I am going to take in the class of electromagnetic wave. Class subject code is EC501. Today's topic is vector calculus. In previous slides we have described what is line integral, what is the significance of line integral, the surface integral and their significance, and the volume integral. In this lecture we are going to understand what is the divergence of a vector, how it works, what is the significance of divergence theorem and divergence vectors, divergence of a vector, how it works, and different examples. So let's begin with the class. First, this is a divergence of a vector. Divergence of a vector is the illustration of the divergence of vector field at point P is this. It means the positive divergence is a outward flux from the point P. Negative divergence is the inward flux, which is, it means the directions of the vectors are in the inward flux towards the P. And the zero divergence means the net amount of flux towards P and the net amount of flux outward of P is same. That's why the zero divergence. It means the divergence means the diverted vector field from the specific element P. If the vector elements, the direction of the vector elements are going outward from the vector, it has been described as positive divergence. If the vector direction of the vector quantities, the direction of the vector quantities is inward or towards the point P element, towards the point P or the element P, it is described as a negative divergence. So let's go to the next slide. And the divergence of a vector, the divergence of A at given point P is the outward flux per unit volume. Now we have, if we recall that the surface integral, it has been described here. It is a surface integral of vector P at point vector A at point P. Now, as we have already described, what is the surface integral is? Surface integral means the outward flux of the specific vector A, which is continuous at the space or the region or the surface S. We have already described that if there is a vector which is continuous in a space S, now if we take the surface integral of vector A at vector A on the surface in which that vector is continuous, we will get the value of we will get the if we take a surface integral of vector A at the surface S in which that vector is continuous, we will get the net outward flux which is going out from the surface A of vector A of net outward flux of vector A from surface S. Now by doing the surface integral, we will get the net outward flux from the surface S. Now if we divide that with del V is nothing but the total volume of that surface. Now as we have taken a closed surface integral, it means it will represent a net outward flux of vector A from that specific volume. Now if we divide that this this mathematical representation by del V. Del V is nothing but the total volume of that specific region where that vector A is continuous. Now if we take a closed integral of vector A on that specific region, we will get the net outward flux from that space. Now if we divide that with the total volume of the specific space where this vector is continuous, we will get the net outward flux per unit volume. So the divergence of a at a given point P is nothing but the outward flux per unit volume, and that has been described using this. Divergence of A can be written as del dot A. A is the vector that is continuous in the surface S or in the volume space V. Now del is the del operator, and it has been mathematically or physically represented as this. Limit del V tends to 0. It means we have taken a very infinitesimal small area or volume or space. We have taken a very infinitesimal small volume in the space where this vector is continuous. So this is the total mathematical representation of divergence of a vector. It means divergence of a vector is basically the at a given point P is the outward flux per unit volume. Let's go to the next slide. Now divergence of vector continues. This is what the A dot ds is a vector field A at closed surface S, and this is the point P. This is the closed surface. This is the representation of dx, the infinitesimal small value along the x-axis, infinitesimal small value along the z-axis, and infinitesimal small value along the y-axis. Now this is the volume. This is the total volume dx into dy into dz. Now if we multiply all these three, we will get the total volume. Now if we divide A dot ds, the closed integral of A dot ds, by the total volume, we will get the divergence of a vector. It means the net outward flux per unit volume. Now now if we have to take a closed integral, how will we do that? Now this is an enclosed surface. Now how are we going to do that? We'll take all summation from front to back, left to right, and top to bottom. It means front to back. It means from this zone, from this point to this point, we'll take a integral. We'll take an integral from this point to this point, and we'll take a integral of left to right from this point to this point. That has been described here. It is from front to back, left to right, and top to bottom. After taking the whole integral, we will after providing the all limits of x along the x-axis, along the y-axis, along the z-axis, we will get the value of total surface integral of this value, and V is the volume of the enclosed by surface S. Now this is the closed surface, this is the whole surface, and this is the volume of. If we take a cylinder, we can take a cube. Suppose there is a flask or jar, so it will in a cylindrical format. The surface, the outer surface of that specific flask, the outer surface is the whole surface that has been closed. The specific volume is S, and the volume that has been enclosed within that surface is V. And this is the in divergence of vector for Cartesian coordinate system is del dot A. it will act as a this way, the del a suffix x by del x, del a suffix y by del y, plus del a suffix z by del z. This is for Cartesian coordinate system, and this is for circular cylindrical system. We got del dot a y by rho, del suffix del rho, rho a suffix rho, plus 1 by rho into del a suffix phi by del phi, plus del a suffix z by del z. This is for circular cylindrical coordinate. And for spherical coordinate system, we got del dot a is 1 by r square, del by del r is will operate on r square into ar plus 1 by r sin theta, and del of del theta will operate on a suffix theta into sin theta, and plus 1 by r sin theta it will operate on the del by del into del phi will operate on a suffix phi. So this is for Cartesian coordinate system, this is for circular cylindrical coordinate system, and this is for spherical coordinate system. For all these function, the del operator will be same. Now here are some example. Here are some example of divergence of the different kind of vectors. This is p is equal to x square yz a suffix x plus xz a suffix z, q is equal to rho sin phi a suffix rho plus rho square z a suffix phi plus z cos phi a suffix z. Another is w, which is equal to 1 by r square cos theta a suffix r plus r sin theta cos phi a suffix theta plus cos theta a suffix phi. Now all these vector that I have described here, the divergence of vector, we are going to take a we are going to solve this example one by one. And one thing that we have to remember, the divergence of a vector, the resultant, if we divergence of a vector will result in a scalar function. Now the first example that we have here is x square yz a suffix x plus xz a suffix z. Now if we have to solve that, now use divergence for Cartesian coordinate system. What will happen? For x-axis we have this, and for z-axis we have xz. So the del operator will operate on first the del of del x is equal to x square yz and plus del of del y, and we don't have any value of y in this. In y coordinate this vector has no value, so it will be 0 and the result will be also 0. And for del of del z, the value is xz. Now the difference, the derivative of this will result in a partial derivative, and the function, the only thing that will operate on the del of del x will operate on x square, so the value will be 2x yz. These are constant, and in del of del z it will operate on only z, the x will be constant here. So the resultant value will be 2x yz plus x. This is the first one. Now we will find the divergence for circular cylindrical coordinate, the same thing, and this is from sorry, this rho phi and z will provide us the conclusion that this will be. Now we have to find the divergence of this vector. This vector is operating on cylindrical coordinate system, so here we will use the del operator, which is applicable for circular cylindrical system. And this one is this rho qp, this is the function. Now put it at place. This is the rho sin phi, rho square z a suffix phi, and z cos phi a suffix z. Now a suffix rho, that function will operate on del by del y, and we have rho square sin phi. Sin phi will be constant, this function will be constant here. Rho square will, after the partial differentiation, we will get 2 rho, the rho and rho will got cancel out, and the resultant value will be 2 sin phi. Now here answer. Hmm. Okay, yes, right. For this value, del suffix del phi, the function will operate on only phi function, but in this, in along the phi coordinate, there is no function of phi is present. The function is the function contain only rho and z, so the resultant differentiation value will be 0. Now the del of del z will operate on z cos phi, where z will become 1 after the differentiation and the cos phi remain constant. So this is the resultant vector for circular cylindrical coordinate, and this is for spherical coordinate. Now also from this function we can understand that r, theta, phi, these three are the vector which are present in spherical coordinate system. So the del operator, which is applicable for only spherical coordinate system, will be operate on this specific vector which is present in spherical coordinate system. And the same thing we will this is the vector that we have already described. What the vector is for circular coordinate system, we have this is the divergence of vector. These are the del operator. The specific del operator will operate on divergence of vector. So 1 by r square del suffix del r will operate on this. We will get the value of, and wr is cos theta. So the r square will be here. The same thing. These are r sin theta, a sin theta. And it will operate on 1 by r square wr. Value of w is cos theta. So these are 2r. 2r and r will be cancel out. This is r sin theta. So there is no r function of r is not present anywhere, because this function is 1 by r square cos theta. So r square will come down and theta is constant, so del of del r will be resulting 0. In r sin theta, w theta will be r sin square theta cos phi, and the value of w phi is cos theta. So the resultant vector will be 2 cos theta and cos phi, because this one is constant, and only this function is also constant because there is cos theta, but the function will be operated on phi, so this is constant, and this function will get down to 0, and after operating on r sin square theta cos phi, we will get this one. It means in case of each and every vector has a different, for Cartesian coordinate system we have a different divergence of vector. In the circular cylindrical system we have del dot a. So all these are operate on different space. For spherical, the divergence of vector is different, the function is different. In case of Cartesian, the divergence vector is different. Del dot a value is different for spherical, for circular, and for Cartesian coordinate system. So these are the examples. Now we describe the divergence theorem. Now what is the divergence theorem basically means? It means it states that the total outward flux of a vector field A at the closed surface S is the same as the volume integral of divergence of A. It means suppose A dot ds, we take a closed integral of A dot ds. Now the total outward flux of a vector field A. Now total outward flux of a vector field A can only be described using this closed integral of V. A dot ds, if you take a closed surface S, that if we take a closed integral of A dot ds, it will provide us the net outward flux of vector field A at the closed surface S. Now if we take a volume integral of the same thing, that is the same as the volume integral of the divergence of A. Now if we take a divergence of, if we take a volume integral of a divergence, then volume integral of a divergence and the surface integral of A dot ds is same. Basically, if we take a surface integral of a closed path, what we will get the net total outward or net outward flux of vector field A from the closed surface. Now the closed surface is basically defined a volume. If you have a closed surface, it means it contains a volume, because a single surface can't close the. Suppose this is a plane, this is a rectangular plane. Now the rectangular plane is not closed. Now if we have to close that surface, we have to draw a line from one path to another path. Now this way the whole surface is closed. Now if we take a surface integral of a closed surface, we will get the net outward flux. Is basically the net outward flux of a specified volume, the region which has a volume, and in that specific region the vector field A is continuous in that specific space. So this is basically described, basically closed integral or closed integral of a closed surface integral of vector A will define the net outward flux from that specific region which has a specific volume V. This is the volume V. Will be equal to the divergence volume integral of a divergence of A. If we take a volume integral of a divergence of A, it will also provide you the same result or the same significance. It means the volume integral of a divergence of a vector will provide you the net outward flux. The same thing will also applicable for the surface integral, closed surface integral of vector field A. It will also provide you the net outward flux from that specific region. And the volume integral of a volume integral of a divergence of a vector A will also provide you the same result. It will also provide you the net outward flux of a vector field A from a closed surface S. So this is the divergence vector. So we will end this lecture of divergence vector from the remaining curl law vector, the Laplacian of a vector field will be discussed in the next lecture. Okay, thank you all.